flames in spacecraft to guide strategies for extinguishing accidental fires. The new Sapphire experiment is going to be hot.
Sapphire is contained inside a 2-foot by 3-foot by 4-foot box that consists of an avionics bay containing the computer and instrumentation and a flow duct which holds the material to be burned. This will be carried aboard Orbital's Cygnus spacecraft during a scheduled cargo resupply mission to the International Space Station. Once at the station, Sapphire will remain on Cygnus until all the supplies are offloaded by the crew of astronauts. Once supplies are offloaded and replaced with trash from the ISS, Cygnus will depart. Once reaching a safe distance from the station, NASA Glenn engineers working from Orbital's Mission Control Center in Dulles, Virginia, will remotely turn on the experiment. Cygnus will then be put into free drift, while the Sapphire experiment is conducted up to 2.5 hours. The experiment's sensors and video cameras are designed to capture valuable data and imagery, documenting large-scale flame spread and material flammability limits. At the conclusion of the Sapphire experiment, the Cygnus vehicle will remain in orbit, while the data captured is downlinked to several ground stations around the globe and transferred to NASA Glenn's scientists and engineers in Cleveland. When downlink is complete, Cygnus will then begin its re-entry through the Earth's atmosphere, where it will burn up over the Pacific Ocean.
Serious. What are we going to do today?
Well, today, first I have to start off by saying that today I'm with someone who needs no introduction, because you've all seen him before. He's the guy we love, Dr. Don Pettit. Welcome to Station Life.
It's good to be back on station. I guess we're really not back on station, but it's good to be here on Station Life.
Thank you, yes. And I am just beyond excited today because Don is not only one of the most fantastic astronauts ever, he's like one of my favorite people. So this is a landmark event in Station Life history that we have with us.
And we both studied chemistry in college.
And look at what he's wearing.
See, I've got my periodic table shirt on.
Okay.
Okay.
Coffee cup.
Coffee cups.
Space cup.
So we have the first generation, the second generation, and both of these have been on station. This is a food-grade plastic, so it meets flight safety and all of that. Here is a variant of the second generation.
What's that for?
Well, this is for Earth, because this is slip cast out of porcelain, and it has this really cool, smooth look that shows off the form and the beauty of the design of this. Yeah, but porcelain is breakable. You can make these sharp shards, and in a weightless environment, they could float around. They could get in your eye, or even worse, you could inhale one of these seeds and get them in your lungs. So we can't take the porcelain ones on orbit, but they're really cool looking, and we can use them here on Earth.
Awesome. Shall we?
Shall we? Notice your nose goes right in the cup,
right in
and you
there.
get this burst of
Java.
Java.
Yes.
Yeah. Yeah, that's a good mix of cream.
You like that?
Yeah. And let me read what it says. It says Space Cup, and that's the official name of this. That's the op nom for the space station, the official sanctioned space station experiment. It's the name of the experiment is Capillary Beverage.
Capillary Beverage.
And the name of the cup is Space Cup. And then there are the words on it. It says Capillary Experiments International Space Station.
That is so
skeletonized
awesome.
NASA meatball.
This would be a collector's item for sure.
I was thinking, Trace,
makes me want to go back up there.
that if you look at everything that I will have accomplished in my life, in 400 years, nobody even remember that I was even walked the surface of Earth or floated around in space. However, I predict that in 400 years, people living and working in space will be drinking, sipping, and toasting out of cups based on my design.
Yes, and you'll be legend. You are legend. What am I talking about?
They won't remember anything like that. Like, do you remember who invented fire? Let's see, and who invented the wheel?
No.
You see, nobody needs to remember who did these things. The important thing is you got to know how to build a wheel, and you got to know how to control fire, and then your civilization can take off. And in space, you don't need to remember who messed with the surface chemistry to make these, but you need to know that you know how to make them, and that you can use them, and it will help build the civilized nature of human beings interacting with each other when you're in a weightless environment.
Well, Don, I've just had so much fun having you on Station Life and sharing your invention and your passion for science and coffee and bringing people together. And I think you've done that in a number of ways, but none so illustrative as the space cup.
I call this a wrap. Huh?
Me too.
A normal coffee cup or a normal open container just simply won't work in a weightless environment because the liquid will be in the bottom of the cup and you tip it up and it still stays in the bottom of the cup. If you move it around too violently, it'll all splash out and make a big mess. So we end up having to drink our beverages through a straw from a bag. Makes you feel like you're a big insect sucking the juices from another insect. I wanted to see if I could figure out a way to have an open container cup in a weightless environment which would allow you to drink your tea and your coffee in a manner that's commensurate with how people drink their beverages on Earth. Taking some of my surface chemistry that I learned in college, I devised a cup with a special shape. The cross-section looks kind of like an airplane wing where it has a cusp, and the cusp will allow channel flow so the liquid from the bottom of the cup will float up and just park itself right next to the rim, and then you can drink it. And it allows a crew to share a communal beverage. You could share tea. Maybe you just come in from doing a spacewalk or something and you want to celebrate a little bit. If you have a real cup, an open container, it's so ingrained in human beings, it's so ingrained in culture, it adds back the dimension of what it's like to be a human being in a civilized way.
Okay, flames and fluids are acting a little differently. But that's not all. Take a look at how microgravity affects colloids, magnetic fluids, and smart materials.
If you have a smartphone, take it out and run your fingers along the glass surface. It's cool to the touch, incredibly thin and strong, and almost impervious to scratching. You're now in contact with a smart material. Smart materials don't occur naturally. Instead, they're designed by engineers working at the molecular level to produce substances made to order for futuristic applications. The Corning Gorilla Glass that overlays the displays of many smartphones is a great example. It gets its toughness in part from fat potassium ions stuffed into the empty spaces between old-fashioned glass molecules. When the molten glass cools during manufacturing, dense to packed molecules solidify into a transparent armor that gives Gorilla Glass its extraordinary properties. Around the world, designers are working on other smart materials, such as alloys that can change shape on demand, plastics that heal themselves when ruptured, and fluids that obey magnetic commands to flow or stiffen under computer control. One of the greatest challenges in creating a smart material is arranging the molecules. They're so small. We want to create a new class of materials beyond smart. We need genius materials, materials that arrange themselves. The research to accomplish this is already underway on the International Space Station. Dr. First is the principal investigator of an experiment called In Space 3. In the microgravity of Earth orbit, vials of fluid mixed with very small colloidal particles, about 1/millionth of a meter in diameter, are exposed to magnetic fields. Magnetism can be switched on and off again very rapidly. This jostles the particles, causing them to bump together and self-assemble into microscopic structures. These structures can be very difficult to predict, even using cutting-edge models running on supercomputers. Astronauts enjoy watching this process in action through microscopes. Because the samples are backlit by a green lamp, they sometimes call it the green blob experiment. First recently won an award from the American Astronautical Society for his work on In Space 3. Just by toggling a magnetic field, we're learning how to take many kinds of microscopic building blocks and get them to spontaneously form interesting structures. Recently, observers have seen the colloidal particles forming long fibrous chains. First speculates that these could lead to materials that conduct heat or electricity in only one direction. The experiment has also yielded crystalline structures that the team is just beginning to investigate. The fluids underlying these tests are themselves very smart. They're called magnetorheological, or MR fluids, because they harden or change shape when they feel a magnetic field. If you own a sports or luxury car, you might have MR fluids in your shock absorbers. The stiffness of magnetic shocks can be electronically adjusted thousands of times per second, providing a remarkably smooth ride. Similar but more powerful devices have been installed at Japan's National Museum of Emerging Science and China's Dongting Lake Bridge. They're there to counteract vibrations caused by earthquakes and gusts of wind. Some researchers have speculated that MR fluids might one day flow through the actuators and hydraulic dampers of robots, moving artificial joints and limbs in lifelike fashion. Scientists and researchers are using these fluids as a laboratory for studying self-assembly. MR fluids are, by definition, responsive to the magnetic nudging that sets self-assembly in motion. Furthermore, in space, the particles don't sediment out due to gravity. We can study the full 3D evolution of the material. Varying the shape of the colloidal particles, the cadence of magnetic toggling, the temperature of the fluid, and other factors will allow researchers and astronauts to further explore the frontiers of self-assembly. Touch the surface of your smartphone again. That's just the beginning.
As you can see, our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. This work off the Earth will lead to a better understanding of the fundamentals of combustion, surface tension, and colloids in the absence of gravity, benefiting us by helping us to make more efficient combustion engines, better portable medical diagnostics, stronger, lighter alloys, medicines with a longer shelf life, and buildings that are more resistant to earthquakes. Research on the International Space Station continues to improve life here on the Earth. Be sure to stay in touch and follow us on Facebook and Twitter for the latest research news, and don't forget to download our app on your mobile device. Until next time, we're working off the Earth for the Earth.
Понимаете, у космонавта, у астронавта в космическом полете вот есть несколько видов деятельности. Ну и, конечно, на мой взгляд, один из самых интересных видов деятельности на борту — это, конечно, выходы. Когда два человека работают снаружи станции, вокруг не только космос, Земля в стороне. Ну, это задача сложная, ответственная, но в то же время очень увлекательная. В космосе, когда смотришь вокруг, то понимаешь, что это бесконечное пространство, и нет ограничений. Вот есть станция, где ты работаешь, есть земля, 400 километров от станции, а все остальное просто не ограничено ничем. Ну, 6 часов непрерывно работать невозможно, всегда есть какие-то периоды отдыха. И в это время, когда висишь рядом со станцией, смотришь на землю, и там под тобой проплывают какие-то острова, океаны, видишь горы. Вообще ощущение, конечно, необыкновенное. Олег Скрипочка, я космонавт.
Esta es Lola de Plaza Sésamo y Lola está feliz, feliz porque le encanta vivir muchas aventuras con sus amigas Diana y Sandra. Ay, porque ellas son realmente ingenieras de la NASA. ¡Ay, sí! Y trabajan en Marte. ¡Wow!
Bueno, Lola, nosotras no estamos en Marte físicamente.
¿No?
No, Lola, pero sí tenemos robots que están en Marte. Tenemos a Maven y tenemos a Curiosity.
¡Wow! 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 ¿Y cómo puede Lola aprender más sobre eso? ¿Cómo?
Aquí mismo en NASA TV, Lola.
¿Aquí y ahora?
Sí, Lola, estás directo. Ve y di hola.
Ah, sí. ¡Hola! Sí, estás viendo NASA TV.
Good morning. Welcome to NASA headquarters.
Ladies and gentlemen, thank you for joining us.
Tune in on the air, online, and mobile. Always available and always in high definition.